Okay. Hello, everyone, and thank you for being here. My name is Alexander Maurice. I'm at the University of Cincinnati, and I'm here to talk to you today about my work in identifying common student misconceptions. And you will spend most of this talk working on identifying physics misconceptions and pedagogical content knowledge. I'll do a bit of a switch where I'll talk about pedagogical content knowledge first, and then you're going to work on identifying student misconceptions. So just real briefly about me, I've done research on the pedagogical content knowledge of TAs and instructors using concept inventories like the FCI, which I'm sure you're familiar with. I've also designed and conducted workshops on teaching and learning for TAs and instructors. And I've been conducting a semester-long TA training at UC for graduate TAs who teach introductory physics recitations since 2015, since I got here. And one of the main components of that training has been, making sure that they learn about student misconceptions and they develop some pedagogical content knowledge, because there's a lot of research about the positive impact of that. This is a question I always ask my TAs. Is it important to be aware of student difficulties in order to help them learn, or do you think it's sufficient to present material in a clear manner? I assume that if you are all here, you would probably agree that it is important to be aware of student difficulties. So I'll mention a couple of research studies that highlight this. So Krepik and Dean Zolman and Sanjay Rebello did a study on students' understanding of sound concepts from a lecture. So what they did is they asked students 6 questions related to sound propagation. Then the students watched a video lecture that was recorded by an award-winning physics teacher, namely Paul Hewitt, and then they answered the same questions again, right? And the researchers told students that they would be answering the same questions from the pre again, and to pay attention to the lecture and make sure that they see if the question is answered, how many times it is answered, and record the answer. So as it pertains to misconceptions, what they essentially found, and this was one of their big findings, is that students' preconceptions before watching the video lecture actually strongly influenced what they got out of a lecture, to the point where they sometimes, the lecture itself reinforced their own misconceptions. So for example, for sound propagation, a very common misconception is that sound travels slower in solids because, well, it dies quicker. That obviously has to do with the amplitude, but this is a common misconception. It travels slower in solids than in gases. And some students would insist afterwards, after watching the video lecture, who had that preconception, they're like, no, but he said it in the lecture, like he said this, right? So it's really interesting how, preconceptions actually color what students get out of a lecture. And, you wouldn't be surprised that students, learned what they got out of a lecture was, less than what you would expect. And also, this is like the ideal situation, right? It's like you told them exactly what to focus on, you asked them the questions right before, and even in this situation, they gain very little. And Phil Sadler did a really interesting study on teaching content on which there are common misconceptions. So this was a study with middle school students. He had over 9,000 students, I believe, in the study. And what he did is he gave them about 20 questions, multiple choice questions. And then he looked at the ones that had a clear distractor choice, where that distractor corresponded to specific misconceptions that students had. And then he compared the learning gains in classes in which the teachers were aware of those misconceptions. So the teachers answered the questions as well, and they answered what they thought the common distractors were. And if they were aware of those misconceptions, their students did much better on those questions than students from teachers who weren't aware of those misconceptions. And there were very little differences on the other questions that didn't have a strong distractor choice. So he makes the point that, this is a form of pedagogical content knowledge, and it really does influence what students learn. So the basic sort of description of pedagogical content knowledge in a nutshell is the difference between knowing physics and knowing how to teach physics. So it's defined as a subject matter knowledge that's specifically for teaching. It's a form of practical knowledge that's used to guide people's actions, teachers' actions, in highly contextualized settings, meaning it has a lot of useful forms of representations. And it basically describes, like, if you want to teach momentum tomorrow, what do you do, right? What analogies do you use? What illustrations? What examples? What do students do in class? What demos and so on? That's what pedagogical content knowledge is. And in addition, this was something coined by Lee Schulman in the late 80s. He also included in pedagogical content knowledge of what makes the learning of specific topics difficult. And as we know in physics, this relates to students' initial knowledge state, which consists of many misconceptions that can interfere with learning, as we've learned from Kripik's study, and they are very resistant to change, which I'm sure if you've taught physics, you've probably seen happens. Not surprisingly, pedagogical content knowledge has the greatest impact on teachers' classroom activities and therefore their learning, and that professional development programs which emphasize pedagogical content knowledge are more successful. And this is why a big focus of my training in college that I do with the graduate students is specifically to help them develop pedagogical content knowledge. I observe them and it's fairly involved. So one way for you to test your own knowledge of student difficulties and misconceptions is by use of concept inventories. So I'm sure you're familiar with the FCI, but there are many different concept inventories. So to give you an example, here's a question from the TUG-K. This is the test of understanding graphs in kinematics, developed by Bob Buechner. So it gives you a graph of velocity versus time, and for a car of a given mass, and it asks for the acceleration at time equals 90 seconds, right? So acceleration at time equal 90 seconds, clearly the slope of this line. So you find that, rise over run, change of velocity over change in time, and the answer is 0.33. So that's easy enough. But the harder questions is, what do you think the misconceptions are here? And to give you a hint, each of these answer choices comes from a specific incorrect way of thinking that students typically engage. I think one of them is obvious. If you can identify some others, just let me know. You can unmute and tell me why students would get this.
Well, I know my students often say, I thought acceleration was 9.8.
Right. So that makes sense. You guys see how they could get 20? 20 over 90 is which one?
That's A.
That's A, okay. So that's just reading it, the velocity is 20, time is 90, so doing that. How would they get the 1?
That's not looking at the numbers on the axes at all. It just looks like you go up 1 and over 1.
Exactly, 2 boxes over 2 boxes, right? So that's a slope of 1. 9.8 is 9.8. What about 20?
Just read the vertical axis.
Right, at 90 it's 20 and not pay attention to velocity. So that was good. You guys are good. Okay, now the question is, which one do you think is the most common? See an answer for A, you can write in the chat. Seen only votes for A or E. And you guys are good. Yeah, exactly. It's A or E, and A is by far the most common. It's important, I think, to know this, right? Because what are students doing? Doing velocity over time and not paying attention that it's change of velocity over time, right? They're using a formula that doesn't necessarily apply to this situation. So this is a question from a concept inventory, and there are many. If you want to see a comprehensive list, you can follow this link. When I was a postdoc, I spent quite a bit of time surveying the literature, looking for concept inventories. There are a lot that you can probably benefit from knowing about. I'm not going to go into much detail about the process of development of these concept inventories. Needless to say, it's fairly involved because you want to get questions where the distractors correspond to very incorrect ways of thinking that students engage in, and they answer them because they think that way, right? It's not, they answer the question incorrectly for the exact reason that you think, and they answered correctly because they get it right. So that's a very long sort of process, involved process of, including running statistics, changing your items, and so on. But needless to say, the incorrect answer choices typically reflect student misconceptions or difficulties. So we saw this one. Also, you probably identified at some point that students think that constant velocity implies constant force, or that moving objects have a distinct force in the direction of motion, or some from physics too. So my question for you is, can you identify student misconceptions? So we're going to spend the most of the rest of this session just working through some questions. You can copy this link here. I'll put it in the chat so you can see the questions. And I've created polls. Now I'm sharing my screen so you can look at it. Let me copy the link. Whoops. in the chat so you can watch them on your screen. And I've also created polls. I was originally going to use a Zoom poll, but apparently those only work in the main room, not in breakout rooms. So I went and created it and all of that, and then it's like, oh, okay, well, it doesn't work. So instead, I've created a poll on Google, and we'll see, and I'll copy the link in the chat. So first, think about just the first 3 questions. So,
Alex, I don't see the link to the questions yet in the chat.
oh, did I put it? Where's the chat?
You might have sent it to a specific person, not
Yeah,
to
that's probably what happened. Yep, to Jeff Rodriguez, whom we all like. Okay, there we go. And then this. Okay, so can someone test if you are taken to this survey, if you follow the Docs Google link, and then you can vote on which incorrect answer choice you think is the most common. Awesome. So we'll go back to the questions here. So think about, obviously, first, what is the correct answer? And then how could students get each of these incorrect choices and then make your selection for what you think is the most common?
You want us to submit our answer for the first one or wait till we answer
All
all?
three, because they all relate to areas under curves.
Okay.
So eat all 3 and we'll discuss all of them. I'm not sure, honestly, if this poll was the best idea. I thought I could see them in real time. Maybe we'll see how this works for these 3, and then maybe we'll move to discussing each one. Yeah, I feel like it might be better just to discuss each one separately. I don't know. I don't like that I'm just waiting. You want some time? Maybe let's think about this one. So did anyone identify how you can get 0.75? Three-quarters, which is like you're trying to do, it's the slope, right? What about, or the rather trying to do slope, but doing it the other way around, right? Then 1.33. That's the slope. 4. Just reading it off. Then 6 is the correct answer, right? The area under the curve. And then 12. I think Jeff answered 3 times 4. Okay, so out of these, so doing slope incorrectly, doing slope, reading it off, or doing v times t, which one do you think is most common? Some B, E, some for C. Yeah, so it seems like most of you selected E as the most common incorrect one. And so for this question, this is correct. It's selected by 32% of students. This is a sample that included both high school and college students. Some also do select C, as you've identified, but those are most common. And there's B as well, but that's nowhere near as common as the other 2. So reading it off, like we saw for the other question, right? And doing velocity versus time. So students are somewhat consistent in their misconceptions, right? Doing velocity times time is the most common, and reading it off is also common, but not as common. Okay, moving on to this one, which one do you think, or how, give you some time to read it. A is a pretty small increase. C is 0. D is negative. I think these are probably the only ones that you might think. So what do we think here? Which one do you think is the most common? A lot of kids would pick A. And maybe wait for like 10 responses. So A, D. Oops. Right. So the yeah. Now the most common incorrect answer choice for this one is C, and it's C by quite a bit. Like no one is selecting anything else, right? And A is of course the correct answer. So very, very strong distractor. So this would be a question on which Phil Sadler would find that students from teachers who know this would do much better. Okay, last one from this group shows acceleration versus time and asking for the change of velocity during the first 3 seconds. Right, so 3 is reading it off. 4.5 is, of course, the correct answer, area under the curve. 9.8 is 9.8. How do you get 1? B is slope, right? This one I'm honestly not sure where it's coming from, and in all the years I've done a workshop on this, I haven't found anybody who could figure this out. So out of these, doing slope, reading it off, acceleration due to velocity due to gravity, just 9.8, right? Which one do you think is most common? Reading it off. B. Doing slope, maybe. Oh, sorry, B. Some said B, some said C. Yeah, so B and C are fairly common, and the percentages are roughly the same for both of these. Right now, is there a answer choice that should be included in here that we've learned from our previous questions? 9, exactly, right? Doing velocity times time, or doing acceleration times time to do velocity. Yes, and this was an original version of the TUG-K for which I have data. They changed this question and they added 9 meters. They changed this to 9 meters per second. So it's useful to know this, right? The misconceptions are reading slope, just reading the thing off, and doing velocity times time or acceleration times time. Okay, here are 2 others. I think the first one should be pretty obvious. So position versus time. How do you translate that? So of course, the correct answer is moving with a constant velocity, because that's the slope. C might get some kids because it's showing a uniformly increasing graph, right? The object is traveling uphill. Yeah, that's a good point. Yes, Laura, do that and then tell me why. So any votes for this? I've seen 2 C's. Constant non-zero acceleration. So same sort of idea. There's something that's confusing. Yeah. Right. So on this, and I don't want to go back to that to show you the answer choices. What students do, I'm just going to tell you. So 24% of students select C, and this is the only misconception on this. So the superficial, they're seeing a graph that increases, and it's like, well, it's increasing, right? They're not paying attention. This is position, it's showing the position is increasing at a constant rate. Okay, this one is probably going to be a bit more challenging. Just to make sure we all get the correct answer first. So the object doesn't move at first, right? Position stays constant. Then the position decreases, right? You go from a positive to 0, so it moves backwards, and then it stops. So the correct answer here is D. Which one do you think is the most common incorrect answer choice? Can we not? There. Right, this looks like a hill. So A, B, and D, and E all relate to a hill. B. Okay, so I see A's and B's. I also saw C. Mostly A, B though. Any other votes? Right. Okay, so what happened, the most common one here is in a sense similar to this, to look at the graph superficially, moving at constant velocity, then slowing down and then stopping. Similar to this, right? Uniformly increasing and not paying attention to what it is. So to show you the percentages, as I said in the previous one, it was only C, which you all identified, reading it superficially, but it's very similar to this one. It's just reading that graph superficially. So again, this is putting together some high school kids and some college kids. It might be that for high school populations, the percentages of students who are reading it as just a picture are probably more pronounced, but this seems to be a much more common incorrect answer choice. Okay, so moving on to Newton's third law. I think for this one, if you have a large truck colliding head-on with a small compact car, I think we all know that students think what? Right, truck exerts a larger force than the car exerts on the truck, right? Now, what about the 16? That's also a Newton's third law question. So this car is pushing this truck, and they're moving at constant speed. So Jennifer says she hopes no one selects E, but do you think they do? I have many hopes for my students as well. So the amount of force with which the car pushes is less. So some people are saying B. That seems to be the most common one. C, because they're moving forward. Some of you also say E. So it seems like the most common ones here are C, B, and a few notes for E. Okay, one more and then we'll talk about all of them. So here, if a student is pushing another student, the student on the right, or this guy has more mass than this other guy. This guy's doing the pushing. So you think students think neither selects a force, A exerts a larger force, B exerts a larger force, Or maybe A exerts a force on B, but B doesn't exert a force on A. See 2 votes for D. A is heavier and doing the pushing. Yeah, I agree. It might have been better to have B be heavier here. B larger, so requires more force. So it looks a couple of votes for B and more votes for D. You want to do a couple more votes for this? At least they're both live. Okay, so for this, you did get the last one. This is we said the first one, right? The truck exerts a larger force. For the second one, the car exerts. So here, car exerts a larger force because they're pushed to the right. So that's by far the most common. The other ones are barely selected. By the way, these are college students. There are about 800 college students in algebra-based classes. So no one's selecting anything else. And then for D, everybody knows that both students exert a force on one another, but the one that's doing the pushing exerts the larger force. It's in a sense consistent with this, right? The thing doing the pushing exerts the larger force on the thing that is just sitting there. Same thing here, the person doing the pushing exerts the larger force. So in the less typical context, I think people in general have a harder time identifying the misconception. Maybe we have a little bit of time for, let's just talk about 5, just identifying forces. So this goes in a circular channel, and then at the point, or you know what, we have 2 minutes. Maybe it'd be a good idea to stop for questions. Or you're welcome to think about this as well. I don't know, did you like this exercise? Yes, I will provide links to all of this.
I'm wondering if as you learn these preconceptions, what are things that you do to change your teaching?
So it sort of depends on you. I mean, there's many things that are discussed in the literature. So a common thing is the elicit, confront, resolve sort of process where you ask them a question that will bring this to bear, right? They will voice that misconception, and then you can, what you do from there is up to you. Like you can have them discuss with each other, or maybe show them simulations, or it sort of depends on each type of thing, right? So for instance, the misconception that constant velocity implies constant force, one of the things that you can do is you can put a student on a little cart and then have a force probe that you pull the student with, and you can ask another student to pull such that the force indicator stays constant. So it kind of, I think, depends on both your personal style and what it is that you typically do in a class or whatever, and what the literature suggests. But at the very least, I would suggest students being active and making sure that to a certain degree that misconception is, students are aware that it exists.
So when you say that, do you mean you would explicitly tell your students this is a common misconception after
Not
you've introduced
necessarily.
it? Oh, okay.
No, I would ask them a question and then I would correct, the issues, right? So for instance, with Newton's third law, an extremely common misconception is to think that a normal and gravity are equal and opposite because of Newton's third law. So I ask several questions related to that, and it's amazing. It's like literally the same question. Like a horse is sitting there and then a book is sitting there, right? And even after I explain the first one, right, they got it wrong. Maybe they have a discussion, we talk about it, and then I ask the next one 3 questions later, and then they revert back to, well, they're equal and opposite because of Newton's third law. So I think, eliciting the misconceptions and correcting them, you don't have to say this is a common incorrect way of thinking, right? Because they see it, right? You can show the polling data and so on. And also for Newton's third law, I'm very explicit about, if 2 forces are equal and opposite because of Newton's third law, they have to be acting on different objects. That's something that we typically forget. And you have to be able to phrase them as force A exerts on B and B exerts on A. So, what is the force of gravity? Well, who exerts that force? Gravity. No, it's the earth exerting, leading them through that sort of reasoning. It's sort of individual to the misconception, but students need to be active in answering questions and, sort of bringing out their misconceptions in class.
I could interrupt here, in about 3 minutes, the workshop for Step Up is going to start in the main session. So if people want to head out there and take a quick break and be there, that's great. If you want to hang out here and chat for a bit longer, that's fine too.
Okay, I can tell you real quick about identifying forces of objects moving. I'm sure you all are aware that students tend to identify a force in the direction of motion as a force acting on this. So like this guy is moving this way. So they know that there is a force the channel is exerting, the centripetal force. Well, it's really a normal force, but they'll call that. And then they will identify force in the direction of motion. Same thing with a hockey puck sliding on a frictionless horizontal table. The most common misconceptions is you've got gravity, you've got normal, and a force in the direction of motion. Same thing here, you have a tension acting in the string. They don't really answer centrifugal force, which I find interesting. The most common is tension, and then gravity, and of course, a force in the direction of motion. This is an extremely common misconception. I'm sure you've seen it. Well, I don't want to keep people if we need to go to something else. Thank you for your attention. I see people are already have gone. Okay,